Hi everybody. In part 2, we're going to see how to estimate the confidence interval for the population mean from a normal distribution. Okay, so by the end of this week, you should be able to calculate and interpret a confidence interval for the population mean of different levels of confidence using normal distribution. You should be able to estimate the sample size needed for a given confidence interval for a specified interval W. And finally, you should be able to interpret how the sample size affects the width of the confidence interval for the population mean. Okay. Before that, I want you to read these questions and answer the question on the side, please. Good. 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 Okay. So the last class, in the last part, you have seen that when the population mean is known, in most of the situation that happens, you're not sure of the population mean, or you do not know the population mean. Yeah, we do not know the population mean. Or if the population mean is varying with time, in such situations, we have seen in part 1 that what do? We try to calculate the sample mean, and from the sample mean, try to estimate the population mean. Yeah, so that's what you do to estimate the population mean. So let's imagine that we have an observed value of the sample mean, and then let's use this to estimate the value of the unknown population mean. Okay, we know that for a sampling distribution, we can state a sampling distribution such that X bar is a random sample mean, which follows a normal distribution with a population mean mu and a variance sigma square by n. And we have also seen that we can transform this sampling distribution into a standard normal distribution using this transformation formula. Yeah. So what is the standard error here for the sampling distribution? Good. It is, the standard error is sigma by root n. This is also called standard deviation of the sampling distribution. Yes, that's right. Okay. So now if you want to be 95% confident that our actual true population mean lies within a certain limit, how will you find the limit? So to understand this, let's sketch the normal distribution. Yeah, that is, we want to be 95% confident that our population mean lies within this limit. Okay, that means there is every 5% chance that the population will not lie within this limit. Okay, let's do that. See, remember, we know the X bar because we know the sample mean. Yeah, we can add up all the data values and divide it by the size of the sample, and we'll get the sample mean. Sample mean is known, so sample mean is known. Z is not known now. Sigma is known, n is known, sample size is known. Okay, so you have seen that if we know the probability, we can find the Z value from the Z table. Yes, from the Z table, you can find the you can use this probability value, find the Z value, and then estimate the population mean. Okay, let's do that now. Yeah? So this means Z value gives you the Z table gives you the Z values, the probability for positive Z values. So to the left, okay? So what will you look for? 95% plus 2.5%. So that means probability of Z less than Z is equal to 0.975. Yeah, 0, because 0.95 plus 0.025. Okay, so you get 0. So look for this on the Z table and you will find Z is equal to 1.96. Okay. Yeah. So if Z is 1.96, by symmetry, minus Z will be minus 1.96. Yes. So now this means our population mean will lie between minus 1.96 and plus 1.96. And and by what percentage are we confident about this? 95%. So there's 95% chances that the true population mean will lie between minus 1.96 and plus 1.96. So now we have the Z value too. We have two Z values because this is the limit within which our population mean will lie. So if we substitute this into this, we can find the unknown population mean. That means we can estimate the unknown population mean. Okay, we can estimate the interval of the unknown population mean. So substituting that, you get this, and then you rearrange to get the limit on this side, yeah, for the population mean. Similarly, when you substitute minus 1.96 in this formula, you get the other extreme. So now you got the two limits for the population mean. Yes. Okay. So these two values for the population mean represent the extreme values, limits for the population mean for 95% confidence, because you are 95% confident. Yeah, because this value used is for 95% confidence. Okay. In other words, mu is likely to exist between these two values with 95% confidence. This gives us a confidence interval within which we would expect the population mean mu to exist with a probability of 0.95 based on the observed value of the sample. Yeah, based on the value of the sample mean which you have calculated from the sample. Yeah. Okay. Now, remember, the population mean is unknown. That is why you're trying to find the limits within which our population mean can lie. Yeah, because in real world you may not know the population mean. Yeah, or the population income for example, in manufacturing industries and other places, the population mean varies. Yeah, so take shampoo bottle. Each time the company produces the shampoo bottle, the population mean may vary depending on the sample or from one bottle to another. Yeah. So sample mean will vary, of course. So the population mean can vary with time. Yeah. Okay. So if you repeated the experiment several times for a large number of times, the sample statistics would represent the population parameters for 95% of the time. Or in other words, for 95% of the time, the true population parameter will lie within this interval estimate. Yeah, within this interval estimate. Yeah. So it gives us a degree of uncertainty, yes, of an estimate, and helps us to decide how precise a sample estimate is. And in other words, a confidence interval is an estimated interval of numbers for the population mean, or is an estimated range of values of a population parameter calculated from a sample statistics. So in our case, since we are trying to estimate the limits for population mean, we can say that a confidence interval is an estimated interval or estimated range of values of the population mean calculated from the observed sample mean. Okay. For the given level of confidence. Okay. Now we know what is a confidence interval for a given level of confidence, and you know how to estimate it using normal distribution. Let's go deeper into it now. Yeah. Okay. So in general, we can say that a confidence interval for this population mean for a size n can be given as this. Okay. Okay. Now, I want you to look at the Z table. What is the probability corresponding to the Z equal to 1.96? That is, I want you to find what is the probability of Z less than Z equal to, oh no, sorry, let me erase that. I want you to find what is the probability corresponding to Z. Sorry, this one. I want you to find this value. Okay. Good, yes. It is 97.5% or 0.9750, isn't it? But we are looking at 95% confidence, and you're getting a probability for 97.5%. Our LOC was 95%, 95% confidence. Why do you think it is like that? So let's go back and look at the distribution again. Yeah. What did we do here? We are talking about the 95% level of confidence or 95% confidence. Yeah. What did we do here? We looked at the Z table to the left of 1.96, isn't it? So it is 95 plus 2.5. So what we did here was we tried to figure out the Z value, the probability for 0.975, because it is to the left of the Z. You have what percentage of data lies to the left of the Z? It is 0.95 plus 0.025. And that is why, even though the level of confidence is 95%, the value of Z we used for 95% confidence is for 97.5% probability. Yeah. Okay. So we have a term for that, and we're going to see that now. Yeah. Before that, can you please choose the right answer here? For 95% confident, what is the Z value, this value? Yes, that's right. Yeah. Good. Yeah, this is because it's based on the sampling method you choose. Yeah, there is always an uncertainty associated with it. Okay. Therefore, a 95% confidence interval, yes, you have a 2.5% of tail on each side. See, 2.5% on this side, that's for 95%. Yeah. And the confidence interval is given as between x bar plus 1.96 times the standard error to x bar minus 1.962 times the standard error. So this value of Z is called the critical value of Z. Okay. Yeah. So that's what I was trying to tell you. Yeah. So this value is called critical value of Z, which corresponds to the 97.5%. Yes. Okay. Now, similarly, if you want to be more confident that the interval includes the actual mean for the population mean, you can use wider limits by using even smaller probabilities in the tails on each side. Yeah. So for example, to increase this confidence level, that is to make it to 99%, you want to increase the confidence level, then you should decrease this value, the value in the tail. Say 2.5 to 0.5%. You decrease the value to 0.5%. Now your confidence interval will be 99%. Let me show you how the distribution will look. Yeah. So that means you have a confidence interval of, that is in the tail, you have 0.5%, 0.5%. You have increased the limit now. You have widened the distribution. So you only have 0.5%, 0.5%. So what percentage are you confident now? You're confident by 99% now. So by decreasing the percentage in the tail, you can actually widen the limits, and you can be more confident that your population, true population mean, will lie within this limit. Okay, so in that case, you have to look for the Z value. Now you have to look for probability of Z less than Z is equal to 0. Because it's 99%, 0.99 plus 0.5 which is nothing but oh dear. Okay, 0. Sorry, it should be 0.05. See, this is a mistake you can all make, yeah? So be careful, guys. For a minute, I was saying, oh, what is this? Probability is going above 1. So 0.995. And if you look into the Z table for this value, you will get a Z value of 2.576. So that is the critical value of Z for 99% confidence. Critical value of Z for 99% confidence. Okay, 0.5% is nothing, 0.005. So that's what you look for, Z table. Okay. Now you know what is the critical value of Z? Yes. Okay, so now we know for 95%, yeah. So let's say that, so for 95% confidence interval, the critical value is 1.96, and we have seen that for 99% confidence interval, the critical value is 2.576. Okay. Okay, now what I want you to do is, I want you to help me fill this table. So we've seen for 95%, the critical value is 1.96. Critical value of Z is 1.96. Let me put a C here. Critical value of Z is 1.96. What is the critical value of Z for 90% level of confidence? Good, 1.645. Similarly, what is the critical Z value for 99% level of confidence? Good, 2.576. So what you can see here clearly is that for 90%, the critical value for Z is 1.645. For 95%, it is 1.96. For 99%, it is 2.56. It's diagonally, yeah? Yeah. Below that is the Z value. Directly below that is the Z value. Directly below that is the Z value. Diagonal value is the critical Z value. Okay. Okay. Now let's solve a problem using all this understanding. So that's your question. Given X follows a normal distribution with a population mean mu and a variance 2 square, where the population mean is unknown. If a sample size of 16 value gives a mean of 10, determine a 95% confidence interval for the population mean mu. Okay, how will you do this question? How will you solve this question? Simple. Write down this first step, write down, state the sampling distribution, sketch the distribution, so you get an idea what you're doing. And then for a 95% confidence interval, for the population mean, what is the interval? How is the confidence interval given by? You remember X bar plus or minus 1.96 sigma by rho 10. And then What is X bar? X bar is, that's X bar. That is 95% confidence interval is used to find the critical Z value, which is 1.96. And this gives you sigma is equal to 2. And that's your N value, sample size. So when you substitute all those, you can find the interval, solve this using a calculator. This clearly means that you are 95% confident that your population, true population mean lies between this. Okay, and after that, you have to interpret what you've calculated. Okay, you have to clearly say what it really means. There are two things you can understand. There are two important points you can interpret from this interval. One, yeah, before that, this is how you should write a confidence interval, okay, with a bracket in, yeah. Okay, so two important points you can interpret from that. One, we are 95% sure that the true population mean, true value of the unknown population mean lies within this interval. And at the same time, there is 5% chance that the true value will lie outside the interval. So these 2 points you should clearly interpret in your solution. Okay, now let's talk about the sample size for a specified interval with W. Okay, we know that for 95%, in general, the confidence interval is given by that. Yeah, okay, this is sigma. Okay, so we know that in general, the confidence interval lies within this limit, and where X bar is the central value. Yeah, it's always centered on the observed value for sample mean. Yeah, and the lower value is called the lower limit of the confidence interval, and upper value is called the upper limit of the confidence interval. Now, the width is nothing but this minus this will give you 2z plus sigma root n. Yeah, you can just subtract it and see. So x plus root, that is x bar plus sigma times z times sigma root n plus, minus x bar plus sigma to find the width. Now you cancel it. So you get 2z times sigma by root n. So that is the width of this interval. Okay, so now you calculated the width. So for a confidence interval to be a specified width W, we can solve the following equation to find the sample size to achieve it. Yeah. So if n is unknown, sample size is unknown, you can use this formula to find the value of n. Okay. So let's summarize it. For a 95% confidence interval for the mean of the population, the mean lies within this limit, and the width will have a width. The required sample size can be found using this formula from the width. Okay. Okay. Now let's see this formula. Yeah. This question. It's nice. Yeah. A manufacturing process produces components whose length L millimeter is believed to be distributed normally with a mean 160 and a variance 4 square. What size of sample would be required for a 95% confidence interval to be no more than plus or minus 1.5 millimeter? So that is the width they're talking about on either side of an observed sample mean. Okay, so that's your sampling distribution. It's given. The normal distribution is given for you. So you have to state the sampling distribution from there. Okay, and sketch the distribution clearly, and then substitute the values. Okay. So here it is plus or minus 1.5. So be careful. That means on this side, it is 1.5 mm. And this side, it is 1.5 mm. Plus 1.5 mm on the right of the 0. I'll put 0 because it is Z, isn't it? Population mean is Z. Yeah. So 1.5 mm on the right and 1.5 mm on the left. So total width is 3 mm. So you put 3 over 2 is equal to 1.96 sigma by root n. So 3 over 2 is nothing but 1.5 is equal to 1.96 times 4 over root n. Okay. And then you rearrange to find the value of n. Okay. You get the value of n. Now remember guys, you can't leave this value just like that because n is a sample size and sample size can be only integers. It cannot be decimal numbers, yeah? So it has to be integer. So you have to round it. So in this case, you will round it up. Why? You'll round it up to 28. Why? Because if you make this value, look at this formula, yeah? If you, in this formula now, look at this formula. If you make this value 27, because it is 0.3, if you make it 27, what will happen to 1.5? What will happen to the width? Good. The width will increase. The width will increase. And you don't want that. It says that no more than 1.5 mm. Okay? And therefore, you have to round it up to 28. So if you decrease the value of n, what will happen? Width will increase. Yeah. And then this will be okay then. It will agree with the question, no more than plus or minus 1.5. Okay. So why? Because a sample size of 27 will make the interval slightly larger than plus or minus 1.5 millimeter. Okay. Okay, good. So we've seen confidence interval. Now we'll see more problems in the seminar. That's all for now. Thank you.